Hello everyone, this is Group 47 here to present the paper Lifelong Domain Adaptation via Consolidated Internal Distribution by Muhammad Rostami. The first problem, domain shift. The primary challenge over here is that the data distribution of new tasks differs significantly from the source distribution. And this variation or a mismatch causes a drastic drop in the performance when applying a source trained model to a target domain. The second problem being manual annotation. That is, when we are obtaining a labeled data for each new domain, it has to be done manually, which is costly and impractical, especially in dynamic or large scale environments. And the third problem is catastrophic forgetting. Neural networks, as mentioned earlier, tend to override the model which is learned from previously existing data or knowledge. And as a result, as the model is trained, it leads to degradation on the earlier tasks, which makes it difficult to retain the accumulated knowledge. Now, given the problem setup, we have two domains, source domain and target domain. Source domain consists of a labeled dataset which is drawn from a distribution P naught of x, with our goal being to minimize the empirical risk. And the target domain consists of sequential unlabeled datasets with a unique distribution, with the constraint or the catch being that there is no access to the past datasets during continual learning. So the solution which we are considering consists of three main strategies. One being the Gaussian mixture model representation to estimate and consolidate internal feature distributions. Second being the alignment strategies to align the target domain with the features of the source domain's internal distribution. And third being experience replay to store and replay representative samples to mitigate the catastrophic forgetting. Now during training, the input data is mapped to an internal distribution in the embedding space. And by aligning this distribution across tasks, we ensure that the model retains its generalization capabilities. And we are using a GMM to represent the internal distribution, with each component in the GMM corresponding to a class, preserving the knowledge structure. The GMM has k components, where each component is modeled by a Gaussian distribution with parameters alpha, nu, and sigma. So our approach in doing this is to first generate samples from GMM and label them based on the model predictions, using a confidence threshold to filter out the low quality samples. Next, we align the target's domain distribution with the internal GMM based distribution. So what this does is effectively minimize the discrepancy between the source and target domains, which enhances the adaptation. And the loss function which we have chosen will combine the supervised loss and domain discrepancy loss, ensuring that the model adapts effectively without forgetting the past tasks. Now the final loss function balances three components, one being supervised loss, which maintains performance on a previously learned task using replayed samples. Second being domain discrepancy loss, reduces the difference between target and internal distributions. And replay loss, which reinforces past knowledge by reintroducing stored samples during training. Together, these components ensure that the model adapts to new tasks while preserving performance on earlier tasks. So in terms of architectural overview, we are essentially training based on label source domain, where the GMM model estimates the distribution of features in the embedding space, And as new target domains are introduced, the model aligns them with the internal distribution, and key samples from the previous tasks are replayed to prevent forgetting. For the theoretical foundation, we frame our analysis within the PIC learning framework, where we are considering a hypothesis class H, given below, and the empirical distributions for the source and target domains, as shown. Now, Theorem 1 provides an upper bound for the expected error across tasks. It includes empirical error, Wasserstein distances, and continual learning contributions. Now, some key insights would be the internal distribution minimizes empirical error, aligning the target distribution as said before, reduces the domain discrepancies, and analysis is storing more samples in the replay buffer, and this improves performance, which aligns with our empirical findings. Now, for empirical validation, we evaluated our model using 4 benchmark datasets. 1. Digit recognition, which consists using MNIST, USPS, and SVHN, which we performed on sequential tasks such as SMU. Now, image CLEFDA evaluated on domains like Caltech 256 and Pascal VOC. And then we use Office Home and Office Caltech. These datasets present significant domain gaps, testing the model's robustness in challenging settings. Now, those results are displayed in the next slides. Now, let's get an overview of the results. Talking about the learning curves, we observed that there was an initial performance drop where domain shift causes the initial drop, but performance quickly recovers due to the knowledge transfer from previous tasks. Now, the model also maintains stable performance on earlier tasks, showing knowledge retention, which demonstrates effective mitigation on catastrophic forgetting. And regarding the dataset complexity, datasets having larger domain gaps like Office Home, the performance improvement is small but still significant. And these results validate the robustness of our model in handling complex domain adaptation scenarios. So, in conclusion, this model is offering a comprehensive solution for domain adaptation in a continual learning setting, where the internal distribution is consolidated, which ensures tasks share a consistent distribution. And we are taking care of experience replay, which prevents catastrophic forgetting. And the future directions, we are aiming to refine the internal distribution estimation, which explores the impact of a task order and also extend the approach to incremental learning for new classes. Thank you for going through the entire presentation, and we look forward to addressing your questions.